And I'm measuring the voltage across the resistor. And I have 1,000 hertz going into the circuit, and the signal is about, let's see, 2 volts. Okay. I'm using a generator that's back here behind the scope that you see there. All right, and the circuit is, I can see my finger. Circuit is essentially below the scope. You can see it right here. That's the circuit. Okay. And I'm going to vary the frequency so you can see how the phase between the power supply. The power supply voltage, by the way, on the screen is in yellow, and the voltage across the resistor is in orange. In fact, let me do this. Let me make the two the same height. Okay, I got them the same height now. And let me increase the frequency. Oops. I'm increasing too slowly, sorry. Do you see the peaks shifting more and more as I increase the frequency? I'm all the way up to 25,000 hertz. And you notice that so now that the inductor is dominating, essentially these are about 90 degrees out of phase. Do you all see that? Okay. So, unfortunately, when you do the RLC lab, you will not be able to see this because you don't have a scope like this one. Your scope only has one input channel, right? This guy over here that you're going to be using has only one input channel. So all you're going to be doing when you do the RLC lab is just to monitor the power supply voltage. This is really what you want to use for that experiment. Unfortunately, we don't have that ability to do that. And again, you know, if I reduce the frequency, let me go back and change. Oops. You see that the phase shift essentially goes to 0. So at low frequencies, there's essentially no phase shift. All the voltage is across the resistor. But at high frequencies, most of the voltage is across the inductor, and so that's where you see essentially the 90-degree phase shift. Okay. All right, so I kind of wanted to show you that. I think what I'm going to do is I have several things I need to cover. So first thing is I want to talk about the lab. So let me change from the camera to the lab itself. This is not meant to be a very long lab. By the way, I am, like I said, I'm still grading your DC circuit analysis lab. I'm actually kind of going through all your calculations. I want to make sure that everybody did things correctly. That's why it's taking me a long time. Most people have done a good job on it. And most of the data, most people have good data. Maybe there's 1 or 2 exceptions, but most people have really good data for this lab. So overall, you've kind of done a pretty good job on the lab. This one really is a lab where you're learning how to use the scope. Okay, there's one feature on scopes that you won't be using because this scope doesn't have it. And even if it did, it would be very difficult to work with. And I'll tell you about that in a minute. So we're going to look at RC and RL circuit. We're going to skip part 3 of the lab. And the reason why is because the inductor that we have is too small for you to observe the effect. The inductor you have is 1 millihenry inductor, and I needed a 10 millihenry. We needed a 10 millihenry inductor, and we're trying to save money, although inductors aren't that expensive, especially these. And so I would choose the 1 millihenry inductor, and unfortunately, it doesn't work for this lab. So we're going to skip part 3. And part 3, all you had to do is just to demonstrate something, and I'll talk about that later. So we're going to use the scope to look at transient circuits. And I showed you the RL circuit with the square wave function a while back. So you're going to set up basically a circuit with a resistor and a capacitor, and a circuit with a resistor and an inductor. So there is a little bit of theory for you to do in here, and I'm going to go through the theory so you can actually do it yourself. Okay, but the procedure is to set up a circuit and then measure the voltage across the capacitor on the scope. Okay, and then we're going to collect some data from the voltage across the capacitor to actually measure the capacitance. Okay, so let me go up to the board. Again, you're going to use those little proto boards, and you'll set up your circuit. It'll be a square pulse, because if you use a pulse that's not square, you know, look at it on the scope. You look at use a battery, the signal on the scope is going to be really boring. Okay, so your resistor, your capacitor, and then you're going to put the scope across the capacitor. And the scope is going to measure the voltage as a function of time. And it'll look like this. And you're going to do it for 3 frequencies. Okay, you're going to do it at 3 frequencies because we want to see, does the frequency make a difference? So the goal is to measure the capacitance from data obtained from scope. That's our goal, okay? Our goal is to measure C from the data obtained from the scope. So we need to know the voltage of the signal generator. So you're going to be using the little signal generators again. And then, you know, for my demo, I wasn't using, the demo I just showed you, I wasn't using the signal generator because my concern about the signal generator is they don't draw enough current. Okay, so you'll be using the little signal generator that you use for the oscilloscope quiz. So that's going to be this guy, and you're going to set it to square pulse. And then you're going to observe the signal on the scope across the capacitor. So how are we going to get data? Well, we derived the equation for the voltage across the capacitor. terms of the supply voltage way back. Okay? And from this equation, we can actually determine C, as long as we know R. So you're going to measure R. And we're going to look at this. In fact, we don't even need to know this, but it's probably a good thing to know what it is, and you can measure that on the scope. And again, we have a one-channel scope, so you can really only look at the voltage across one item at one time. Okay, so if you want to look at the signal across the scope, you got to take the leads on the scope and connect them directly to the signal generator. Or you can take the leads from the scope and connect one point here and one point here in your circuit. Okay. So what I'm going to do is the following. I want to say, at what time is the voltage across the capacitor half the maximum value? I want to look at this. I want to look at what voltage, or at what time is this equal to a half? And I'm going to call the time at which this occurs T1/2. We also do this when we talk about radioactive decay. Okay. And we call it the half-life. Anyway, so let's solve for T in this case. So I'm going to move the 1 to one side. And I'm going to cancel out the minus signs. And then I'm going to come down here. I'm going to take the natural log of both sides. Oh, I took a natural log. Sorry about that. And I'm going to get rid of the minus sign. And so C ends up being the time at which you get half the maximum voltage and the times R, natural log of 2. So what you're going to do is measure the time it takes. It doesn't matter which side, but you want to measure the time it takes for the voltage to be 1/2 its maximum value. Okay? So you're going to measure T1/2. You're going to measure R, and you're going to calculate C. That's it. It's just T, yeah, this T is T subscript 1/2. Okay? It's T subscript 1/2. Which is very hard unless I write giant. I don't have a lot of space on the board to write that big. Okay? When people talk about half-life, they use the T1/2. Okay, so it's consistent. That makes sense? So that's all you have to do. But you're going to do it for frequencies. You're going to do it for 3 different frequencies and see if it makes a difference. You're going to do it at 100 hertz, 500 hertz, 250 and 500. You'll do it at 3 frequencies. The question is, does the frequency at which I do it make a difference? Now, There is another way that we normally do this. What we do a lot of times is, I mean, when we're on ground, when we're in the lab and we do this, we use a feature that the scope has. There's a probe on, there's a button on it. If you pull the button out, it expands the horizontal axis by a factor of 10. And what you can do by doing that is actually measure the slope of the voltage as a function of time at any particular point. And usually what we do is we measure the slope at this point. So if you take the derivative of this function take the derivatives as a function of time and set t equals 0, you get a real simple expression for calculating c. All you have to do is measure the slope at t equals 0. Well, we can't do that with our scope. Okay? And I'm mentioning this to you because you need to know this, that there's a little button on the scopes, and the normal scopes you can pull out and expand the horizontal axis by a factor of 10. And then you can measure C from that. And you can do the same thing for the RL circuit. Okay, so that part we're skipping. Right? I do want you to be aware of that one can do that. So what we're observing here is the transient response of the circuit to this varying power supply, and this is the response. Okay, so we're really not looking at the steady state case because the circuit never has a chance to reach steady state. We're just looking at the transient response. Does that make sense? So that's all you have to do. So all you need is your little protoboard with the resistor in series with the capacitor, and then this guy and this guy. That's really all you need. Okay. The second part of the lab, we're going to replace this with an inductor. Okay. And we're going to go through the process. So in part 2, the goal is to measure L maybe this is better. The goal is to measure L from the data obtained from the scope. Now, for part 2, we know that the current is given by this equation. And pay attention to these derivations. These are the derivations I want you to do in the lab. Okay? This first equation which I derived is in the theory section that you're expected to derive this. Okay? And the other theory thing we're going to do is derive the equation for the voltage across the inductor. Okay. Again, we're going to measure R, and we're going to measure to determine the inductance. We're going to measure also the voltage when the time in which the voltage across the inductors would have its maximum value. But this doesn't give me the voltage across the inductor. So the voltage across the inductor is L di over dt, which is L. Now, what's the time derivative of this? Well, it's going to be R over L, because when I take the derivative with respect to time, I'm going to get an R over L out. And then the minus signs will cancel. These L's cancel. This R times I max is really the power supply voltage. And really I should use deltas. Sorry. I hope this color is not too light. Okay. And again, your signal is going to have this kind of form. And so the question is, I want to find the time in which the voltage across the inductor is 1/2 its maximum value. Let me get a darker color. And so I set delta V sub L, and it should be delta, sorry. Take the log, again, take the log of both sides. Again, the subscript is 1/2 on the T. I get rid of my minus signs here. So L ends up being R times T 1/2 over natural log of 2. So I measure the time in which the voltage is 1/2 the maximum value. I measure R, and I just use this equation, and I get L. Okay, so one thing. The inductor is 1 millihenry. This is the inductor you're given. Set the frequency to 5,000 hertz, and then okay, set the frequency to 5,000 hertz. The original document said 500 hertz, but because the inductor is too small, is a factor of 10 too small, we have to set the frequency to 5,000 hertz, otherwise you're not going to be able to do the lab. Okay, you're not going to get anything measurable. You're not going to get the greatest results from this. I mean, you'll probably get within 15%. Okay? I don't think, you'll be lucky if you get better than 15%. Just because of the precision of the scope and the rate at which the signal dips. It dips very quickly because of the value of L and R that we have. Okay. Questions? So remember, 5,000 hertz. Not 500, 5,000. And if you do, look, if you're, as I was grading the labs, there was some data that looked, one or two folks had horrendous data, and they never questioned it, and they never asked the question. Your job is if you have bad data, you got to talk to me because I don't know if that means your equipment's not working. Okay, and if you just leave it, then that tells me you don't care. Okay. And yes, Matthew, you're only doing one frequency at 5,000 hertz. That's it. Okay, in part 2, one frequency at 5,000 hertz. Okay. Yeah, I just want to. Yeah, I want to make clear that I've changed it to 5,000 because I still gotta. I think I still gotta send you the update, an updated version. Okay, because some people will forget, so I want to say it several times. Whereas in part 1, you're doing 3 frequencies. Here, you're doing 1 frequency. Okay. But if something is not working right, your results don't make sense. You got to contact me because if you just leave it and you get harmless results, it just tells me you don't care. Okay. So this one, if you're getting bizarre results like 1,000% error, 100% error, you shouldn't get 100% error. Okay, you got to contact me, and that will help you. There's one or two you actually did a Zoom session, and I had the student show me their circuit, and we tried to troubleshoot the circuit to make sure it works. So we can make whatever arrangements are necessary to make sure your circuit works. I want your lab to work. Okay, so I'll do whatever I can to help you. So if your results are bad, please contact me. Okay. Okay, so the third part we're going to skip because the inductor is too small. So what does the inductor look like? That's the question. What does the inductor look like in your lab kit? So if you had a resistor, if you had something that looked like a resistor that was like 1 ohm, that was the inductor. So let me switch cameras, and I'm going to show you what the inductor looks like. So let me put the circuit in front of the camera. This is my RL circuit that I used. It's a little fuzzy because of my hand shaking. You see the thing on the left that looks like a giant resistor? That's actually an inductor. Okay? That's actually an inductor. So that big thing that looks like a resistor is really an inductor. The color code is brown, black, red, and gold. Okay, brown, black, red, and gold. The big resistor, that's an inductor. Okay, and if you measure its value, the resistance will be like 1 ohm. They'll tell you that it's not a 1,000 ohm resistor. Okay, they'll tell you something's wrong there. Okay, so that's what you want to use. You want to use, that's the inductor you will use in your circuit. Okay, it's where they look like resistors, but that is an inductor. It's a 1 millihenry inductor. Okay. All right. So it turns out, and I didn't know this when I created the lab, that the multimeter that you got, this multimeter that you got could actually measure capacities. The one that we were originally going to purchase did not have that feature. So, if you want to get probably better results, you'll probably want to measure the capacitance of the capacitor. All right, because when you read the capacitance rating on them, they'll be within 20% of the value. So to get a better value, better results, you can actually measure the capacitance value. So where it says in the lab, it'll say, hold on a second. the C labeled. In the lab, it'll just say, what is the, it'll tell you about the labeled value. Like, let me just go to the document. In the lab here, it says percent error from C labeled. You can just measure that. So yeah, Patrick, it is 1,000 microhenries on the inductor. So anyway, the percent error C labeled, you can measure that with this. Now, you cannot measure inductance with this meter, unfortunately. Neither this one or the one I originally had, we couldn't measure inductance. So in the case of the inductor, we have to go with the labeled value, which is 1 millihenry. Okay? But you can measure the capacitance of the capacitors. So take advantage of that because that'll probably give you better results. Okay? Are we okay on that? Because I made some changes, I'm saying several things over and over again because I want to make sure there's nothing gets messed up. Okay. So you can see your write-up is not too complex. It's not like the DC circuit lab. I mean, you do have to do some error analysis in here, but it's not too complex. Okay. Because, here, let me show you the equation on the board. The error analysis on this is not hard, all right, because you just have a product of two numbers. Okay. And the error analysis for the RC circuit is not complex, it's simple. So the error analysis is pretty straightforward in this lab. There's nothing too complicated. And you're only doing 2 out of the 3 parts. In fact, the third part, all you have to do is take a picture. Okay. Any questions on this lab? I want to make sure everyone's clear because you only have until December 1st to do this lab. And it's possible that if you do something wrong, you might get bad results. If you have bad results, you want to contact me. I really want to make sure that you guys understand how to use the scope. Especially for those of you guys who want to be electrical engineers, you got to know how to use a scope, okay? So I'm going to try to, I haven't emailed you the new version of the lab because I changed 1 or 2 things because of the minor changes here. But we can't do part 3. So this part's not, unfortunately, we're not doing this part. But I'm going to talk about it today. Okay. Any questions? Yeah, yeah, Patrick, no part 3. And I tried to do part 3 with the potentiometer. Because the inductor was too big, I tried to use the potentiometer to do part 3, but the potentiometer is like 1 turn, and so the resistance varies. The adjustment in the resistance is really coarse, and so I couldn't get it to work either. So yeah. You can play with it if you want. I mean, you can try it, but I think if students tried it, they would have too much trouble with it. So I figure skip it. But you can give it a shot if you want. But I think you need to do it correctly, you need about a 20 ohm resistor. And to set the potentiometer to 20 ohms or 25 ohms is tough. But it's just so coarse. Okay, any questions or concerns? I just want to make sure everything's clear. The instructions are all clear on here. Yeah, if you can do that, Patrick, go ahead. It's kind of cool to see the underdamped case. I'm going to show you a picture of it a little bit later. So like I said, there's 2 theory parts. Make sure you do the derivations. I think this is the only time this semester I'm having you do a derivation. So when you do a derivation, you should kind of explain what you're doing. Don't just put a bunch of letters there. Just like how you guys ask me questions about the letters on the board, I expect you to tell me what the letters stand for in your derivations. Imagine if your textbook was just a bunch of equations. You think you'd be able to learn from the textbook? Assuming you read a textbook. It's hard, right? It's hard. It would be hard to learn from a textbook if you just saw a bunch of letters in equations. So I don't, I just write a few little notes next to the equation saying what you're doing, so that the reader can understand. Remember, when you're writing these lab reports, you're writing to a peer. You're not writing to yourself. Okay? And you're really not writing to me, but you're writing to someone who's at your level. Okay, you're writing to someone who's at your level, who might be able to do this lab. Okay. All right. So I want to talk about LC circuits. Driven with a power supply like a battery. So let me draw a circuit on the board. Okay, suppose I have the following circuit. Now look, what I'm going to be doing here is highly idealized, okay? And I probably wouldn't even be able to demonstrate this. Well, I for sure couldn't demonstrate the ideal case, okay? But let's say I have a power supply. I have a switch here. I have an inductor. And I have a capacitor. Okay? Now, I close the switch. Tell me what happens. What do you think happens in this case? Well, at t equals 0, all the current goes through the capacitor, because this doesn't like a change in current. And so at t equals 0, everything goes through here. But as time passes on, as this capacitor builds up, the di dt here gets smaller. So then current's going to be allowed to pass through here, and then less current will be allowed to pass through here. And as you get to t equals infinity, all the currents goes through here. This acts like a wire at t equals infinity. So all the current goes through here, and this is fully charged. Now, what if, assuming an ideal inductor, assuming that the accelerated charges in the wire do not radiate from the circuit, what happens now when this is fully charged and I open the circuit again, open the switch again? What happens? The capacitor will discharge. The capacitor will discharge and transfer its energy through the inductor, but the inductor has no resistance. So the current will build through the inductor as this thing gets discharged. So this is dumping its energy, this is starting to store energy. Once all the energy is stored up in this thing, Then the energy is going to go back into the capacitor. The capacitor, because once this thing has all its energy in here, and this has no energy, this is going to dump its energy back into the capacitor. It's basically like a mass on a spring. Yeah, the capacitor discharges through the inductor. And what you have is this, as long as no energy is lost, you have this cyclical process where the energy is transferred between the capacitor and the inductor. Just like how kinetic energy passes into potential energy and vice versa on a mass on a spring problem. Just give me a second, I want to switch microphones. Okay. So what are some important equations? Well, let's consider the total energy. Energy is conserved here. How long will it last in the non-ideal case? And that's going to depend on the resistance. And so what will happen is in the non-ideal case, which I'm going to do next, you'll get a decaying, your amplitude will decay exponentially. And how that decay transpires is going to depend on how big R is. If R is really small, you can actually see the decaying. If it's underdamped, you'll see the decaying exponential in the sine function. And so I'm going to do that next. I'm actually going to set up the RLC circuit with the transient response. So the total energy is conserved, and the total energy goes between the capacitor and the inductor. And so the energy in the capacitor is Q squared over 2C. The energy in the inductor is 1/2 Li squared. So suppose I take the time derivative of this equation with respect to time. Since no energy is lost, the time derivative of the total energy has to be 0. So let's take a look at this equation for du dt. So we wrote down and this has to be 0 because the total energy loss is 0. There's no resistor and there's no radiation. We're assuming there's no radiation lost to the accelerating charges. Okay, so if I take the derivative with respect to time, I'm going to get 2q dq over dt. Remember, q depends on time, so I have to use a chain rule. Let me simplify some things. Let's see. I get and this is going to give me L times I di over dt. But dq dt is I, so let me just write that as I. Oh no, let me not write that as I. Di dt di dt is a second derivative of q. So I can rewrite the equation in the following way.
these terms cancel. And so I get Q over C plus L times d2Q over dt squared equals 0. Let me isolate terms. How do I solve that for Q? Well, because of the fact, and normally you would say, oh, I'm going to integrate twice, but I can't do that because I don't know explicitly what Q is as a function of time. However, you guys can solve this. I know this is a Math 33 problem, but I know you guys can solve this. You know why? Because what this says is what function I can take the derivative twice, get the same function back times a negative of a constant. What function can I differentiate twice and get the same function back times the negative of a constant? What do you think? Okay, yeah, e to the ix, so, but it's sines and cosines, right? Yeah, when you say e to the ix, that's and you're writing sines and cosines in terms of complex exponentials. Okay, so basically the derivative of a sine or a cosine is going to give you what you need. Now, you can write the general form in this manner. It turns out you can write Q in the following two ways. You can write the solution Q or you can write it this way. You can put a sign there too, it doesn't matter. And A and B, or Q and delta, are just constants that are determined from the initial conditions. Normally we use this method. It is more convenient to write it this method because then you can see the phase shift in your function. Okay, so we're going to write it that way. So you can write it either way. Okay, so what's omega? Well, if I take the derivative of the function twice, here I'm going to get 1 over LC. So that means that omega has to be equal to 1 over the square root of LC. So this is the characteristic frequency of the circuit. Okay, so omega is the angular frequency. And so dq dt is basically omega q max times sine of omega t plus delta. So we need to set some initial conditions to determine delta and q. Well, let's say that q is q max, which is true in the way that we set up our circuit, and I equals 0 at t equals 0. Then delta has to be 0. I mean, think about it. If I plug in t equals 0 here, the only way for this thing to give me q equals qm is if delta is 0. So this tells me qm is the maximum charge of the capacitor and delta m is 0 given our initial conditions. You're going to get a lot of practice doing these kind of problems in Physics 215 or in Math 33. Math 33, basically you spend a lot of time dealing with the initial conditions to find your constants of integration. Okay. And so then the current is going to be minus omega q max, if you take a time derivative of q, times sine omega t. Why the minus sign? Because the minus sign represents the fact that the capacitor is discharging and the I and the Q are 90 degrees out of phase. So let's take a closer look at the energy in the system. The energy is always conserved. Maximum energy stored in the capacitor when the current is 0, and maximum energy is stored in the inductor when the charge in the capacitor is 0. That means that the maximum value of the energy in the capacitor and the maximum energy in the inductor have to be equal to each other, since energy is conserved. And so energy oscillates between the capacitor and the inductor, assuming no losses. Okay, so now what I want to do is the more realistic case. I'm going to get a better marker. I want to do the more realistic case involving the resistor, the capacitor, and the inductor in series. In the example I just showed you, when I opened the switch, the inductor and the capacitor were in series. Well, let's do this case. Actually, let me draw it here. And let me put a switch here. So I want to know what happens when I close a switch. What happens in my circuit when I close a switch? What do we expect to happen? We know at t equals infinity, the current goes to 0. And I'm going to focus on the current in my circuit just because it makes the problem a little bit easier to deal with. Okay? It just makes the math a little bit easier for me if I just focus on the current. Isn't the current going to do this? It's going to start at 0, go up to some value, and it'll go eventually back down to 0, because once the capacitor is fully charged and the energy's used up the energy's used up everything, you're going to get something that looks like this, or it's possible you can get something that looks like this. Okay? Those are the possibilities. So you're going to have some sort of decay in your system. Can I write the equation? Can I apply Kirchhoff's laws? Okay, the modified version of Kirchhoff's laws. I'm going to say the current's going this way, and I'm going to assume the voltage drops in this direction. If I apply the modified version of Kirchhoff's laws, I'm going to get, let's do it this way. Get delta V sub S minus I times R minus the voltage across the capacitor minus L di dt equals 0. I have Q's and I's in this thing. I really want to focus on the current. Okay, I can solve the problem really however I want to do it. Really, I want to focus on the current. So focus on I. And I'm not going to go through all the details of the solution. I just want to understand the physics. Okay, if you were taking Math 33, you would actually go through all the details of the solution. I want to focus on I, and I want to make life easy on myself mathematically. Okay, I can solve this problem. I would have to write everything in terms of Q, and I can solve it. And the graph you see in the bottom left-hand corner represents Q as a function of time for this circuit. But I want to solve for I as a function of time. Just because the math is easier. Okay, you'll get a graph that looks similar to that. So this is what I'm going to do. Take the time derivative of above equation. So if I take the time derivative all the way across, what am I going to get? This is a power supply that's constant. What's the derivative of constant? Well, it's 0. What's the derivative of this? Well, I'm going to get minus R di over dt. And this is going to give me dq dt. dq dt is I. One of the reasons why I'm doing this is because if I solve it this way, I actually have to think of two different solutions. Okay. Let me cancel out the minus signs. What else can I do? Let me divide both sides by L. There's that factor again. So if R was 0, this guy would disappear. And we'd have the same equation for the LC circuit we had before, except it would be for I instead of Q. Okay? So I know that I goes to 0 as t approaches infinity. This is a Math 32 equation. This is a differential equation. It's a homogeneous second order differential equation with constant coefficients. So I would have to know Math 33 to solve this, but I do have some intuition I can use to solve this. I'm going to guess a solution. I'm going to guess that as my solution. Okay? And if I'm able to figure out A and omega, I'm done. If I can determine A and omega from this, I'm done. So what I'm going to do is I'm going to substitute this function into here. If I take the derivative of this twice with respect to time, I'm going to get the same function back times omega squared. If I take the derivative of this respect to time, I'm going to get the same function back times omega. And then I still have the same function. So all of these terms will still have the same function in it, so I can actually factor out the function. And what I'll get is an omega squared here. I'll get an R over L omega here. And then what I'll get here is in order for this to always be true, the stuff in the brackets always has to be 0. So that means that sets the conditions on omega. There's got to be a set of conditions on omega for this to be true. And so let's find omega. I just got to use the quadratic formula. It's minus b plus or minus the square root of b squared minus 4ac all over 2a. So as long as omega satisfies that condition, then we have that solution. And then A we can determine. Okay, one can determine A. I'm not really that interested in A. Like I said, I'm interested in the behavior in the circuit. So let me rewrite this. I'm going to factor the 4 out of here. Okay? So I'm going to get the following. Those are the values for omega. But there's several things we need to consider. You can have this case, you can have this be bigger than this. You can have this be smaller than this. Or you can have, in the rare case, that to happen. And this is where the interesting stuff comes in when we discuss what these different conditions. Okay, so that's what I'm interested in, is these conditions. So this first case, what if this guy is bigger than this guy? Well, the radical is positive, okay? If this is the case, the radical is positive. And my solution, by the way, I do have two solutions, right? Because I have one where this is positive and one that is negative. So let me write my solutions down. Okay, I need some board space, so I have to erase this stuff. My solution looks like this. Since there's two of them, Oh, there's a T here, sorry. I could factor out one term. Okay. And the A and B's are determined from the initial conditions. So if the first term is bigger than the second term, then what? Well, this is an increasing exponential, but this exponent is bigger than this, so you still have a decreasing exponential. Okay, there's a T here, sorry. So this exponent is still bigger than this one. This is more negative and this is positive, so you still get a decreasing exponential. And then here you have the decreasing exponential. So you basically have a current that does this. Okay, and the current just goes straight to zero, and it decays, current decays exponentially without oscillations. So we call this overdamped. Now the very interesting case is when this guy is smaller than this guy. Then what does that mean? What does it mean when this guy is smaller than this guy? What's going to happen to this if this guy's smaller than this guy? This is imaginary. So you got to write your solution this way. What does it mean when your exponents are complex? Do you remember Euler's formula? You have sinusoidally varying function. So this decays, so you have oscillations. So your current oscillates to zero with the decaying exponential. Now the graph shows you the charge oscillates about a maximum, but the current oscillates about zero. So this case is called underdamped. And so you get a decaying exponential with oscillations. The last case, when these two are equal to each other, then this guy is zero. These two terms are the same, and in order for you to actually, you need to have two terms in your solution because you have two constants of integration. In the case where that's zero, in the case where the exponents are zero, you have to actually go back and redo this. And you get the following. To a solution. This is called critically damped. And the function, the current goes to zero in the shortest period of time. You reach steady state in the shortest period of time. And if you're looking at Q as a function of time, which I can always integrate this, if you're looking at Q as a function of time, then the charge goes to its steady state value in the shortest amount of time. Those are guys who you take physics 215, you're going to see the same form of the equation when you look at the mass on the spring that's damped. And you're going to get a damped harmonic oscillator problem where you looked at critically damped, underdamped, and overdamped. And that has applications, for example, in designing shock absorbers. So what I was going to have you do, and I can't, is to observe this on the scope. So let me show you data I took over the summer. Okay. By the way, this graph shows you the charge as a function of time for the three cases. And I look at the current as a function of time. Just the current is easier to get to. So let me show you a scope trace that I took over the summer. I just got to find a scope trace. That shows you an underdamped system. Because that was my goal. I was going to show you have you look at the underdamped case. So that was the scope I used over the summer, although we got a different scope. And that shows you a circuit that was underdamped. I put in a square pulse, and I chose the right values of R, L, and C to get the underdamped case. So in that particular case, with the value of R, with the value of L, we could not satisfy the second condition that I showed you on the board. But this is the underdamped case. Okay? And this is what I just wanted you to set up an underdamped circuit, and we won't be able to do it. So Patrick, if you have resistors you want to play around with it, go for it. You would probably need about a 25 ohm resistor, and you probably would observe it. Questions? Sorry I went over. I think I've covered everything I want to cover. All right, so if I don't see you in 210R, have a good weekend.